Alright, this is the project file we built in episode 1. About 70 lines of plain text, the entire definition of a heat conduction simulation. Every value, every reference, every choice we made through the GUI ended up here. In this episode, we're going to read this file section by section, so by the end you can hopefully open any Elmer SIF you find and know what each piece does. The file extension is .sif. It stands for Solver Input File. This is what ElmerSolver, the actual numerical engine, reads off disk when you click Run. Everything else in this ecosystem, the GUI, the mesh generator, the result viewer, is built around producing or consuming this one file. A few things to notice before we dive in. It's plain text, it's human readable, it's a few kilobytes. You can open it in any editor, commit to Git, or check the difference between the two versions of it. There is absolutely no proprietary binary blob hiding anywhere. One thing worth flagging up front, the SIF format isn't formally specified, so no published grammar or no standards document. It's grown organically since the mid-1990s. And the de facto reference is the ElmerSolver manual published by CSC. So when we walk through this file, I'll be referencing that manual, and at the end I'll point you to it. So the structure of the file is pretty much uniform. The file is a list of sections. Each section starts with a keyword on its own line. For instance, header, simulation, material 1, or if I scroll down you can see body force 1, and etc. And each section also ends with the word end, also on its own line. So you can see end basically closing that specific section. Between those two you get keyword value pairs. For example, under solver 1 you can see I have a keyword value pair, variable is equal to temperature. If I scroll down under material 1, you can see a keyword value pair, heat conductivity is equal to 51.9. The keyword on the left is basically something that Elmer knows about, and the value on the right is what you are setting it to. Keywords are case insensitive and they are white space tolerant. You will see the same keyword written different ways in different tutorials. The manual writes them with capital initials and single spaces, and that will be the convention we'll stick with. So this particular file has 12 sections: header, simulation, constants, 2 solvers, 1 equation, 1 body, 1 material, 1 body force, and 1 initial condition. We didn't really give any values to those, but we still have those sections. We can easily just delete them and nothing happens. And we also have 2 boundary condition sections. Alright, before we walk through the file line by line, let me show you the shape of what we are doing. On the left of this diagram is what you write. 12 sections grouped into 3 rows. At the top, the whole run settings is where you have header, simulation, and constants. These sections are the sections that apply to the whole run, not to any particular piece of geometry. In the middle, the numbered definitions: solver 1, solver 2, equation 1, material 1, plus the 2 empty sections of the template left behind. These are reusable. They sit declared in space. None of them on their own actually does anything. Down at the bottom in red, body 1. This is the keystone. The body block is where the definitions above get bound to a region of mesh, over on the right. Without the body, the rest of the file is just floating declarations. And below it, the boundary conditions. These don't go through the body, they bind directly to mesh boundary IDs, not to body IDs. Different namespace, same idea. That's the whole structure. Whole run settings at the top, reusable definitions in the middle, right? bindings at the bottom, and we are going to walk through the file in that order, and we'll come back to this diagram a few times along the way. So group 1, whole run settings, 3 sections that describe the entire run, not any particular body or boundary. Let's look at these 3. Alright, let's start with the header. 2 lines. Check keywords warn tells ElmerSolver what to do if it encounters a keyword it doesn't recognize. Warn means print a warning and keep going. The other common values are abort, which is more strict, and silent, which suppresses the message. The more important one is mesh db, and that one has 2 strings, parent directory and the mesh subdirectory. As you can see, we are using quotations, double quotations, and this period here means that the mesh file is located in the same directory as the SIF file. So together it's telling ElmerSolver, look in the current directory in a folder called mesh. That's where the mesh files live. Now if the mesh files are not there, obviously you're going to get an error. So if you put your mesh files in a separate directory somewhere else that is not exactly where the SIF file is, then you have to specify the parent directory and also specify the name of the mesh folder that you are planning to use for this simulation. So you can change the mesh file directly in SIF by pointing at that specific mesh, a file that you're planning to use for your simulation. Alright, the next section is simulation. Let's start from the beginning. Max output level controls how chatty ElmerSolver is in its log. The manual's scale basically tells us level 1 is representing only errors, level 3 is warnings, level 4 is the default, and level 10 is everything. 5 is a reasonable kind of middle ground setting that you can put there. The second line is coordinate system. In this case, we are in Cartesian frame. You notice that there is no 2D suffix here. The dimensionality is kind of inferred from the mesh. The mesh has nodes with x and y, but no z. So ElmerSolver figures out it's a 2D problem. You could go ahead and write Cartesian, something like Cartesian. So the next option in simulation section is simulation type. In our case, we set it to steady state. We want the field at equilibrium, no time evolution. The other major option is transient, which would bring in time step sizes, time step intervals, siblings, and a time stepping method. Then we have steady state max iteration, which we set it to 1. This is the outer fixed point iteration count. The loop ElmerSolver runs to couple multiple physics or to iterate on a nonlinear problem. Heat conduction with constant conductivity is linear, and we have a single physics, so 1 iteration is enough for us. And then we have output intervals, which is set to 1. This writes the result every iteration. For a steady state, that's effectively once at the end. Now if you're running a transient kind of simulation and you don't want to write the output at every single time step, you can increase this value. Let's say you want ElmerSolver to just write the output to your desk for every 5 steps or every 10 steps. Maybe your time steps are too small and you don't want to store every single time step for various reasons, maybe because of the space issues, or you don't even care about those small time steps. Alright, before we move on from simulation section, I want to quickly show you that you can obviously click on simulation section on the outline panel and it will jump to that section. This is true for every section. If you click on that section, it jumps to that specific section. But more importantly, you can see one of the tabs we have at the bottom is simulation setup. And that's where you can set things up for your simulation, including the coordinate systems. You see the list of all available coordinate systems. You can decide if this is a steady state or transient. We'll talk about scanning maybe later in future episodes, and then set everything up for your simulation sections. If I change this, for instance, to transient, you will see that there will be some extra things that we need to set, like as I said, time stepping, and a couple other things that we have to mention for specifically transient simulations, like the method and the order and time step interval and the size. But I just wanted to show you that that's also available, so you don't actually have to edit things in a SIF file. And as I said before, in ElmerStudio there is a tight coupling between the options and the SIF file. For instance, if I change this to Cartesian 3D and I click apply, you can see that it immediately changes to Cartesian 3D. Of course, it's not the right setting for this problem, but I just wanted to show you that you can actually update that specific section by changing the values in this panel. Alright, then we have the constant section. This is basically a simulation-wide physical constants. This template ships with Stefan Boltzmann constant set to its standard value because Elmer's radiation boundary conditions reference it. We are not using radiation, so it sits unused, harmless, and a sensible default to leave in place. Alright, let's look at group 2, which basically are definitions. As we said, we have 5 real blocks and 2 kind of empty ones. The solvers are the physics modules. The equation and material are descriptions waiting to be referenced. And the empty stubs, in this case body force and initial condition, were left by the template, and they don't really matter for this problem. Here they are in the file. Alright, so let's start with solver 1, the heat solver. The number, solver 1, matters. Other sections will refer to solver 1 by that number. Then we have procedure, which is set to those 2 strings, the dynamic library name and the function name inside it. Together, they tell ElmerSolver to load the heat solve module and call its main routine. This pair is how all of Elmer's physics modules are plugged in. You almost never edit it. Then we have variable, which is set to temperature. This is the name of the field the solver computes, and it's the name you will pick from the field drop down in the results viewer. Basically, you can see what you solve for. Then we have stabilize, is set to true. This option adds streamline upwind stabilization. It's relevant when there is a flow field carrying heat around, which there isn't here, but it's safe to leave on heat solver default. Then we have equation, which is set to string named heat equation. This is just a label for this solver instance. Equation blocks below will reference solvers by either their number or their name. The rest is stuff related to numerical methods. We are using an iterative linear solver with a specific preconditioning. It's capped at 500 iterations with a residual tolerance of 1 times 10 to the minus 8. For a problem this small, you could also use a direct solver. The template defaults to iterative because it's what scales typically the best. Alright, next solver is solver 2. This is in physics. It's the result output solver, a built-in utility that writes the answer to disk. Same shape as solver 1, but its job is files instead of fields. Output file name is equal to case and output format is equal to VTU together. They tell ElmerSolver to write the result into a VTU file and put it where the mesh files are by default. And if you go to the mesh file, mesh folder better to say, with all the values there, you will see a VTU file, which is your result file, placed there after you successfully run the simulation. Then we have saved geometry IDs, which is set to logical true. This writes the body and boundary IDs into the VTU file, the result file, so you can color cells by which body they belong to. This is useful when you have multiple bodies and you want to look at the results and kind of identify those bodies. Then we have the option ElmerSolver, which is set to after simulation. This tells ElmerSolver to run this after everything else has converged. So basically run the whole simulation, make sure everything converges and the results are produced. Then run this solver, which basically writes the results to your disk. The other common values are always, before simulation, and before time step. You can take a look at the ElmerSolver manual, and it goes into more details about what each one does and how they affect the execution of this solver. Alright, so I jumped ahead a little bit to look at equation 1. There are two keywords. Active solvers 1 is equal to 1. What this does, basically it says when this equation set is active, run solver 1. And there is a piece of syntax worth flagging there, the parenthesized 1. It's an array size hint. Elmer's parser uses it to know how many values to expect on the right side of this key value pair. If you wanted to activate the heat solver and let's say another solver like a flow solver, we would write active solvers in parentheses 2 is equal to 1 and 3, let's say, if we had a third solver to solve the flow. You will see this same pattern in target bodies and target boundaries shortly later in the SIF file. Material 1 is basically a property bag. We have density, conductivity, heat capacity at the top. Those are what the heat solver reads. The block also carries Young's modulus, Poisson's ratio, thermal expansion, electrical conductivity, and permeability. The full 1020 steel profile. The heat solver ignores those, but if you plan to have a structural solver, let's say tomorrow, it would be able to find them ready and use those values. One important detail I have to mention from the manual: density is mandatory in any material block. So the solver checks for it on parse, even if your physics doesn't reference it directly. So before we actually move on to the next section, I want to quickly mention the material or material section. In ElmerStudio, if you click on the material section, obviously it takes you to where that specific line is, the beginning of the material section. But I want to bring your attention to material library in ElmerStudio, which is basically a panel under outline. If it's not there, you can go to view and check material library. Make sure it's checked, then it will show up as a panel, either attached to this part or maybe floating around. You can put it back here. These panels are they can move around. You can move them around and hook them in different parts of the window. Alright, so if I click on material, you can see that there is a predefined material library. You can choose a specific category to narrow down the list of materials, or you can just keep it on all and select the material from the list. And once you select the material, whatever that material is, you can see the properties predefined in the material library. Now, whether you are adding a new material as a section, or you're applying these changes, or to the material section you already have, you can use this panel. For instance, let's say right now I have steel, and let's say I want to change it to copper. Right, let's say I want to change it to copper temperature dependent material. I make sure that the section is selected in this part that says apply to. Obviously I only have one material section, so there is no other section, and then I can click apply, and as you can see, it immediately changes the values in material 1 section we had. And since this is a temperature dependent material defined that way in the material library, you will see that it defines them in a very specific way. So heat conductivity now is variable as a function of temperature, and then it's given, the values are given as a function of temperature. One nice thing about ElmerStudio is that if you actually come here and click on plot, you can get a nice plot of the material properties that are defined as a function of temperature. So in this case, heat conductivity is defined as a function of temperature. You can see it from 200 to 800 degrees, and also the heat capacity. Both of them are defined for the same range. So I just wanted to quickly mention that. You could also define a new section and add a new material. And if you actually have materials defined in a specific format, which is something that you can import as a JSON file. And finally, the two empty stubs, body force 1 and initial condition 1. These two blocks, basically they start and they immediately end. ElmerStudio's template wrote them in case you want to add a volumetric heat source or a non-default initial temperature later. The manual is clear that both sections are optional. An empty block basically means no body force and no initial condition, which is what we want for a steady state problem with two pin temperatures. You could delete these two blocks and the file would pretty much behave identically. Alright, now the keystone. Look at the arrows here, from solver 1 to solver 2, equation 1, material 1, body force 1, initial condition 1. They all basically point at the body 1 block. This block is where the references converge and where they get tied to a specific region of mesh. Up to this point, everything in the file has been abstract. Solvers, materials, equations as floating definitions. The body block is the first place where the physics meets geometry. 5 keywords we have in this section. There is the array size hint again, target bodies. This block applies to body ID 1 in the mesh. We have one body, so we pass one value. If we had two bodies in the mesh and wanted this block to apply to both, we would write target bodies in parentheses 2 is equal to 1 space 2, something like this. Again, we don't have it here. Alright, last group, the boundary conditions. Notice on the diagram, these don't go through the body block. They bind directly to mesh boundary IDs. If I zoom out, you can see that they are directly connected to the mesh. And notice the call out in the corner, 2 of or 4 mesh edges don't actually appear anywhere in the SIF. That's not a mistake. Let's look at the boundary condition blocks in SIF and then we'll talk about the two that aren't there. Alright, same pattern as before, but these reference mesh boundary IDs and not body IDs. Boundary condition 1 applies to mesh boundary 3, which basically was the top edge of our plate, and sets temperature to 0. Boundary condition 2, as you can see here, applies to mesh boundary 1, the bottom edge, and that one sets temperature to 100. Alright, now if you remember our mesh, we had 4 boundary IDs, bottom, right, top, and left, and you can actually identify them. If I click on the top boundary, you can see in the status bar here that shows this is boundary 3, and if I click on the one at the bottom, you can see in the status bar that is representing this as boundary 1, and we have the ones in left and right, boundary 4 and boundary 2. We have written boundary condition blocks for 2 of them, right? The right and left edges, IDs 2 and 4, were not mentioned in SIF. Now, that's obviously deliberate. In Elmer's heat solver, an edge with no boundary condition block referencing it gets the natural boundary condition by default, which for heat conduction is 0 flux, insulated. You get insulation by writing nothing at all, basically. The empty space is the boundary condition itself, so it has a meaning, and that's why it was not identified. If you look at the outline, part, it kind of gives us a warning that we have also unassigned boundaries, which are 2 and 4. It's nice to see it there, but you know that you left them unassigned unintentionally. Intentionally. So before closing, one thing worth basically mentioning: ElmerStudio treats the SIF as the source of truth and the GUI as a view unto it. Edit the file directly, the form updates. Edit the form, the file updates. Both directions are live. Most engineering tool GUIs generate their input file in one direction only. You edit through the GUI and the file is a downstream artifact. ElmerStudio's model is closer to a code editor with a structured view panel. If you want to go deeper, the document to read is the ElmerSolver manual. This is published by CSC. It's the reference for every keyword that's valid in a SIF, organized by sections. If you open it, it's not the kind of manual you read front to back. You read the chapter for the physics you're using. Look up the keywords you need and add them to the right block. Now in the next episode, which will be your episode 3, will cover mesh generation, building the mesh from scratch in ElmerStudio's mesh generator, going deeper than what we did in episode 1.